These projects are located exactly in the wrong spots. They're in floodplains, thawing tundra, dissolving bedrock, and more. Whether due to poor decision-making or poor planning, here are 15 things that are built in the worst possible locations. Let's start with number 15, the Millennium Tower in San Francisco. When the 58-story Millennium Tower topped out in 2008, its glass curtain wall and $350 million price tag made it the showpiece of San Francisco's South of Market boom. Yet this gleaming blue shaft rose from one of the most problematic geologic settings on the U.S. West Coast, a wedge of bay fill reclaimed after the 1906 earthquake by dumping rubble and dredged mud into the shallow tidal flats of Mission Bay. Geotechnical consultants warned that the fill, underlain by 60 meters of loose Holocene silts, would continue to consolidate for decades. But the developer chose friction piles that stopped well short of the Franciscan bedrock, driven only about 18 to 27 meters to seat in dense sand layers, classified as Old Bay clay. So that decision shaved about $5 million off the foundation costs, but it left a super slender tower dependent on skin friction in soils known to soften when saturated or shaken. Yeah, so all that technical jargon aside, alarm bells rang almost immediately after occupancy. By late 2009, automated survey targets showed that the raft had settled about 25 millimeters. By 2016, the total settlement had reached 400 millimeters, and the structure had tilted 150 millimeters to the northwest, enough so residents on high floors could see a perceptible slope in hardwood corridors. Leaks from a failed waterline in 2014 accelerated the consolidation along the west edge, while dewatering for a nearby subway excavation removed pore pressure and further robbed the clay of buoyant support. Independent analyses were prepared for the city's Department of Building Inspection, and they concluded that nothing in the original design violated the code, but that the code itself assumed the piles would be either on rock or very stiff soil, assumptions plainly wrong for this site. Litigation followed fast. By 2017, more than 250 condo owners had filed against the developer, its geotechnical engineer, and the structural engineer, and the city, alleging that poor siting and value engineering wrecked the property values by up to 30%. A confidential settlement in 2019 set aside $100 million for a retrofit, but meanwhile the tilt passed 0.2%, visible to the naked eye when looking up the building's southwest corner. And even earthquake scientists grew nervous. Simulations at UC Berkeley suggested that a magnitude 7 Hayward fault scenario with 40 seconds of shaking, differential settlement could double, and some perimeter columns could yield unless the foundation was stiffened. Well, the chosen fix, called the Perimeter Pile Upgrade, involved coring 52 concrete piles, 1 meter in diameter, through the sidewalk on Mission and Fremont streets and socketing them 80 meters deep into Franciscan Melange. The steel sleeves then clamped the new piles to the existing mat via a 1.5 meter thick reinforced concrete collar. And because excavation within the basement could jeopardize the existing diaphragm wall, the work proceeds entirely outside the footprint. Crews drill through 2 meters of granite pavers, install temporary casings, and tremi-concrete under polymer slurry to avoid any cave-in. These piles are jacked incrementally so that they pick up about 30% of the building load, arresting settlement and reversing the tilt by an estimated 75 millimeters. As of April 2025, 48 piles are completed, and monitoring prisms show that settlement tapering to no less than 1 millimeter per year, down from the 80 millimeters at the 2016 peak. So all the Millennium Tower saga highlights is why its parcel was ill-chosen in the first place. Seismic microzonation maps published after the 1989 Loma Prieta quake flagged much of south of Market as Zone E. That's the worst classification for liquefaction potential. The city planners approved high-rise developments there only to the presumption that the deep-bearing piles would be used, as they were for the Salesforce Tower 2 blocks away. By deviating from that precedent at a site with no margin for error, the project converted ordinary consolidation settlement into a landmark case of urban engineering hubris. Although the current monitoring indicates the retrofit is working, the final cost is going to exceed $150 million, triple the original savings. And every buyer disclosure in perpetuity must now mention differential settlement. Few structures illustrate more starkly how choosing a cheap foundation in the wrong geologic niche can turn a luxury tower into a cautionary tale that leans, quite literally, towards disaster. Number 14. Kansai International Airport in Japan. Kansai International Airport opened in September 1994 as the world's first long-haul hub built entirely on a man-made island. It's a bold answer to a noise curfew and expansion limit strangling Osaka's landlocked Itami Airport. Engineers formed the 4-kilometer-long island by dumping over 180 million cubic meters of quarry rock and dredged sand onto a seabed of Holocene clay and silt up to 20 meters thick. These are sediments acknowledged even in early reports as highly compressible and prone to long-term consolidation. Designers predicted approximately 11 millimeters of settlement over 50 years, and they tried to preempt it with sand drain wick columns on a 1.5-meter grid vacuum consolidation and a 3-year waiting period before erecting any terminal structure. But the underlying deposit behaved more like toothpaste than soil. By opening day, the island had already dropped 8 meters. Settlement has never stopped here. Continuous GPS benchmarks show an additional 5 meters of subsidence between 1994 and 2025, leaving runway A's centerline 13 meters lower than its initial grade. Now, the elegant kilometer-long Terminal 1 designed by Renzo Piano sits on 900 steel columns mounted to hydraulic jacks that technicians adjust twice in a year. Some jacks have already exhausted 85% of their stroke. Retrofit teams are welding spacer blocks beneath the base plates to regain headroom. To keep the aprons above storm surges, the airport authority has spent roughly 70 billion yen, that's about 480 million US dollars, raising the seawalls and installing 240 meters of sheet pile cofferdams. Yet Typhoon Jebi in 2018 still produced a 3.8-meter surge that flooded electrical substations and stranded 8,000 passengers overnight. But why build here at all? Political pressure for the 24-hour operations made offshore siting attractive, and Osaka's bay shallow depths promised lower dredging volumes. Planners also assumed that state-of-the-art ground improvement would halt subsidence within 2 decades, a forecast now plainly wrong. Subsequent forensic studies by the Port and Airport Research Institute revealed that the clay's high organic content and drainage extending consolidation timelines by a factor of 2. Well, worse, the island's enormous weight, about 500 kilopascals of effective stress, squeezed water out towards its center, creating differential settlement. The east seawall drops 20 millimeters more per year than the west, inducing hairline cracks in the taxiways. While a second island, completed in 2007 to host runway B and additional cargo aprons, used improved techniques, deeper sand drains, phase-wise filling, and a thicker rock mattress. Even so, it settled almost 6 meters, better, but still double projections. Engineers are now injecting cement bentonite slurry beneath a taxiway slab to stabilize voids and mitigate the tilt, while seawall heightening continues at about half-a-meter increments, timed to projections of sea level rise and land subsidence through to the year 2050. But operationally, Kansai does remain safe. Instrument landing systems recalibrate monthly, and the pavement management system grinds high spots where differential settlement exceeds 6 millimeters. Yet maintenance costs are punishing, about 12 billion yen, that's $82 million annually, triple those of Narita, an airport handling similar traffic. The Kansai saga offers a stark lesson in siting. Building on soft marine clay can succeed. Amsterdam Schiphol proves that, but only when load, consolidation behavior, and time horizons are reconciled honestly. At Kansai, early models underestimated the secondary compression, ignoring the acceleration that dredged and surcharge exerts on clay creep, and failed to couple geotechnical predictions to realistic maintenance budgets. 3 decades on, Japan has an airport that works, but costs billions more than forecast and will demand vigilance for its entire service life. Few places show more vividly the price of placing critical infrastructure atop the very ground least equipped to bear its weight. Number 13. The Palm Jumeirah in Dubai. Alright, everybody's seen this one before on Google Earth. Few modern developments broadcast human ambition more loudly than the Palm Jumeirah, that palm-shaped archipelago that extends 5 kilometers into the Persian Gulf off the coast of Dubai. It was conceived in 2001 by state-owned Nakheel as a way to add 56 kilometers of prime beachfront to a coastline barely 1/10 that length. A project requiring dumping over 97 million cubic meters of dredged sand and over 7 million tons of rock onto a coral-fringed seabed no deeper than 11 meters. Dutch and Belgian suction hopper dredgers shuttle down 24 hours a day from borrow pits about 10 kilometers offshore, spraying rainbow arcs of sand in GPS-guided sweeps until the Palm's 17 fronds, the crescent-shaped breakwater, and 6.5-kilometer trunk emerged above the water. Engineers then used vibrocompaction probes to densify the fill, but the location still courts three fundamental hazards: shoreline erosion, water stagnation, and sea level rise. Wave data has showed that the northerly Shamal winds could hammer the unfinished island with 2-meter breakers, so contractors ringed the Palm with a 200-meter-wide, 11-kilometer-long breakwater built from gabbro quarried 140 kilometers away in the Hajar Mountains. Now, this protective crescent does calm the wave energy to lake-like conditions inside the fronds, yet it also throttles tidal flushing. Early water quality studies in 2004 recorded residence times of up to 25 days, high enough to trigger algae blooms and hydrogen sulfide odors. Nakheel ordered 3 100-meter gaps cut through the breakwater and commissioned a pair of 90-meter-wide navigation channels to encourage circulation. While follow-up monitoring by Woods Hole Oceanographic Institution in 2007 showed the average residence time fell to 6 days, but nutrient buildup still periodically boosts the phytoplankton above Dubai municipality's threshold of 20,000 cells per milliliter, forcing temporary swimming bans. Well, if all that wasn't enough, erosion and settlement remain chronic. Hydrographic surveys between 2006 and 2022 reveal that the wave diffraction around the breakwater's tips has scoured channels up to 4 meters deep along the outer crescent, exposing both the core filter cloth and demanding 9 periodic rock armor renourishments at a cost of roughly $30 million. Differential settlement is visible along the trunk's monorail guideway, where the slab track panels have been reshimmed 4 times to restore level. A 2020 LiDAR scan by Dubai municipality measured vertical subsidence of about 4 to 5 millimeters per year. That's modest today, but compounded by the Intergovernmental Panel on Climate Change's central sea level rise projection of about 0.77 meters by 2100, enough to overtop sections of the breakwater during king tides, unless it's elevated. Even the celebrated location imposes logistical penalties. Fuel, groceries, and construction materials must cross one 6-lane causeway and a single 2-track monorail. During peak tourist weeks, the trunk road handles 10,000 vehicles per hour, 3 times the 2003 traffic model. Any serious accident blocks emergency egress for 100,000 residents, hotel guests, and workers. A second sea bridge was proposed in 2016, but it stalled after the cost-benefit studies showed free cash flow payback exceeding 25 years. None of these issues make the Palm Jumeirah uninhabitable. It still remains a luxury address, but they underscore how selecting an offshore shoal in an evaporating gulf creates a permanent engineering treadmill. Beach nourishment barges patrol every spring, subtidal air raiders hum beneath the breakwater gaps, and municipal teams raise manhole rings yearly to keep pace with the sinking pavement. The island's promotional brochures showcase the opulent villas and 5-star resorts, yet behind the glamour lies one of the most maintenance-intensive square kilometers on Earth, a man-made promontory locked in perpetual struggle against the very sea it set out to conquer. Number 12. The Banqiao Dam in China. Completed in 1952 on the Ru River, a tributary of China's Huai Basin, Banqiao Dam embodied the Mao-era ambitions to tame floods and power rural electrification. Soviet engineers using advanced earth-fill structures 118 meters high and 488 meters long, with a clay core and a design flood capacity of over 1,000 cubic meters, adequate, they believed, for the region's most severe rainfall on record. A storm in 1933 that delivered 300 millimeters of rain in 3 days. Yet the chosen location lay squarely on the western flank of Typhoon Alley, a corridor where Pacific cyclones sometimes stall against the Tongbai Mountains, dumping double that volume in less than 24 hours. Hydrologists in the Ministry of Water Resources cautioned that extraordinary storm number 12, a 1954 event of 600 millimeters, should guide the spillway sizing, but political pressure to finish quickly and conserve steel kept the crest outlet to 6 sluice gates. Well, during the Great Leap Forward from 58 to 60, the site's vulnerabilities deepened. Upstream catchments were also stripped for backyard iron smelters, increasing the sediment flow, while the dam managers, under quotas to maximize irrigation, kept the reservoir near full pool through monsoon season. A reinforcing project in 1961 added a sluice tunnel and raised the crest by 3 meters, yet the maintenance budgets collapsed during the Sino-Soviet split. Piezometers failed, the clay core cracked from differential settlement, and seepage drains clogged with silt. By August 1975, Banqiao's design flood discharge was down to 500 cubic meters, half its original capacity. On the evening of August 5, 1975, Typhoon Nina's remnants collided with the cold front and stalled over the Ru Basin. Local gauges recorded over 1,000 millimeters of rain in 24 hours, 3 times the dam's design and a modern Asian record. By midnight, Banqiao's reservoir surpassed the super check level, the water overtopped the emergency spillways, and it scoured protective riprap from the upstream face. Operators then radioed for permission to open all the gates, but received no reply. Telegraph lines were already down, and diesel backups at the dispatch center had failed. At 1 a.m. on August 8th, the dam's clay core liquefied at a 70-meter head, creating a breach 300 meters wide. A wall of water 6 to 9 meters high raced downstream at 50 kilometers an hour, collapsing Shimantan and 60 smaller dams in a cascade. The flood's kinetic energy matched over 2.5 megatons of TNT, and it scoured a 55-kilometer-long channel into the plains. Official tallies released in the 1990s attributed 26,000 immediate deaths to drowning and another 145,000 to famine and disease in the months that followed, making Banqiao's history the deadliest dam failure of all. More than 11 million residents were displaced, 5.9 million houses destroyed, and 3,000 kilometers of railway swept away. An investigative commission concluded that inadequate spillway capacity, silted drains, and reservoir misoperation turned an extreme but foreseeable typhoon into catastrophe. They also pinpointed a siting error. The dam lay below the confluence of the 3 tributaries, draining steep, deforested slopes, funneling runoff more rapidly than any model used in the design. Reconstruction started in 1993 to replace Banqiao with a concrete gravity dam featuring gated spillways sized for over 12,000 cubic meters, 10 times the original. Yet the geography hasn't changed. Hainan remains vulnerable to sailing typhoons, as the 2021 flood underscored. Modern flood manuals teach Banqiao as a worst-case study and worst location siting, when a major hydraulic structure sits at the mouth of a flash flood-prone mountain catchment without redundant discharge. No amount of earth-fill compaction can substitute for topographic reality. Banqiao's grassy slopes now appear peaceful, but the stone monuments at the visitor center reminded engineers and tourists that choosing the wrong valley can turn a promise of prosperity into one of the deadliest civil engineering failures ever recorded. Number 11. Benito Juarez International Airport in Mexico. When Benito Juarez International Airport welcomed its first DC-2 in 1931, it sat on the northeastern fringe of a modest capital in the high plateau of central Mexico. The site, however, was anything but stable. It lay on the silty remains of Lake Texcoco, a shallow endorheic basin that Spanish colonists had begun draining 4 centuries earlier. Beneath the runway asphalt, water-saturated clays as much as 60 meters thick exhibit liquid limits over 250% and shear strength so low that a child's footstep can leave an impression after heavy rain. Geotechnical studies performed for runway extensions in the 1950s warned that long-term consolidation would continue for, quote, generations. Yet planners preferred the convenience of proximity to the city center over relocating to firmer ground. Subsidence was immediate and relentless. Between 1931 and 2024, the airport plate area has sunk more than 15 meters, 4 times the settlement of New Orleans, and twice that of Venice, because Mexico City simultaneously withdraws about 60 cubic meters of groundwater from the same aquifer that once supported the lake. Differential movement is the real menace here. The western threshold of runway 5 right now sits about 1.5 meters lower than its eastern counterpart, creating a longitudinal slope approaching the 1% limit by the ICAO. To keep glide paths within tolerance, the Federal Civil Aviation Agency has milled and relayed asphalt keystone wedges on more than 40 occasions, each time shaving high spots and feathering new layers to restore a flat profile. Radar calibration towers have to be re-shimmed annually. Approach light stanchions stand on telescopic steel bases that technicians have to jack downward as the ground drops beneath them. The surrounding city does magnify the risk. They handle about 49 million passengers a year on a footprint 1/3 the size of comparable hubs, leaving no room for any new taxiways or stormwater basins. Few airports better illustrate how a geologically unsuitable location can trap a megacity in perpetual crisis response. The airport still functions, graced to obsessive resurfacing, adjustable structures, and flight operations all choreographed that squeezes 60 movements an hour from intersecting runways. But every new millimeter of settlement tightens the bind between physical limits and urban demand. No amount of asphalt can make clay hold still, and every aircraft that roars skywards is a reminder that the busiest airport in the Spanish-speaking Americas rests on a ground that quite literally cannot support its weight. Number 10. The Mosul Dam in Iraq. Standing 113 meters above the Tigris River and impounding a reservoir 48 kilometers long, Mosul Dam is Iraq's largest hydroelectric and irrigation structure. It's also, according to the U.S. Army Corps of Engineers, the most dangerous dam in the world because its engineers in the late 1970s placed it on top foundations of gypsum, anhydrite, and carbonate strata that dissolve on contact with water. That choice was driven by politics and haste. Planners wanted the dam close to Mosul's power grid and assumed that a positive cutoff grout curtain could isolate the soluble layers. Soviet consultants warned of pervasive karst voids, some more than 2 meters wide, yet construction began in 1981. Mosul Dam is an earth-filled structure with a central clay core and rock shells, designed to deliver 750 megawatts through 4 Francis turbines. From first filling in 1985, water did find its way through fissures and began dissolving the gypsum, creating sinkholes downstream as large as 10 meters. To slow the process, Iraqi crews injected a cement bentonite slurry into a 200-meter-long gallery drilled 45 meters beneath the core. Grouting has become a full-time, never-finished job. By 2024, workers have pumped more than 48,000 tons of grout, that's enough to fill 18 Olympic pools, into the foundation. Yet the voids keep reforming because groundwater flow continually leaches new channels. Mosul Dam is a stark emblem of flawed siting, a massive hydraulic structure built on top rock that dissolves in water, maintained by a perpetual race against geology and time. Modern instruments can map the voids and grout can slow dissolution, but neither can rewrite the mineralogy beneath the core. In effect, every cubic meter of water stored is balanced against a ticking chemical reaction underneath, a Faustian bargain that obliges engineers to keep pumping cement indefinitely, or accept the risk of a flood that could redraw Iraq's map in a single day. Number 9. The Love Canal Neighborhood, Niagara Falls. In 1894, an entrepreneur named William T. Love began digging a power generation canal on Niagara Falls' east side, only to abandon the project when financing evaporated. The incomplete trench, a 300-meter-long, 20-meter-wide clay basin, stood empty until 1942. The Hooker Electrochemical Company then bought the parcel and began dumping chlorinated hydrocarbon waste into the pit. Over the next 11 years, Hooker entombed roughly 21,000 tons of mixed chemicals, including dioxins, hexachlorocyclohexane, benzene, and polychlorinated biphenyls, under clay caps that are only 1 meter to 3 meters thick. With post-war suburban growth surging, the company sold the filled site in 1953 to the Niagara Falls Board of Education for $1, inserting a single page rider noting that the buried chemical drums remained and they disavowed liability. The board promptly built the 400-pupil 99th Street Elementary School directly on top of the canal and encouraged developers to ring it with 800 modest track houses. The location's flaws surfaced almost immediately. Spring thaw raised groundwater that leached through the fractured clay caps, flooding basements with black, oily liquid. Children playing behind school in 1968 discovered rusted drums protruding from the soil. Workers simply pushed them back and covered the area with fill. By 1976, local reporters had cataloged birth defects clusters, epilepsy, liver dysfunction, and miscarriage rates twice the state average, all within a 4-block zone bordering the canal. Environmental chemist Lois Gibbs, a resident whose son attended the 99th Street School, petitioned state agencies for soil tests. Investigators from the New York State Department of Health found hotspots of dioxin exceeding 100,000 parts per billion, orders of magnitude above any then existing guideline. Love Canal's legacy reaches way beyond Niagara Falls. Congressional outrage over a suburb knowingly built on toxic waste catalyzed the 1980 Comprehensive Environmental Response, Compensation, and Liability Act, or the Superfund, which has since financed cleanup more than 1,700 sites nationwide. And Hooker's successor, Occidental Chemical, eventually paid $233 million in restitution, the largest environmental settlement of its era. Yet the Love Canal endures in civil engineering curricula as a case study in catastrophic siting, a school and neighborhood purposely erected on top of one of North America's worst unlined chemical landfills, proving that location mistakes can turn everyday homes into toxicological landmarks whose cleanup costs dwarf any short-term savings. Number 8. Centralia Borough, Pennsylvania. All right, Centralia. Well, we've talked about this one before. It began in 1866 as a typical anthracite mining town that straddled Pennsylvania's Mammoth Coal Seam, the continent's thickest hard coal deposit. Every backyard sat within a few meters of combustible carbon, but for nearly a century the geology posed little existential threat. Mining happened in deep shafts and a network of gangways ventilated by upcast furnaces. By the 1950s, though, most collieries were abandoned, and the borough opened a rubbish tip in a 20-meter deep strip mine cut at the town's south edge. The pit connected to the old workings through fissured sandstone, and on May 27, 1962, volunteer firefighters burned trash in the pit to reduce volume, unknowingly igniting a coal seam exposed in the rubble. Flames crept through the fracture and dropped into the abandoned Buck Mountain bed, entering a labyrinth of oxygen-rich voids beneath the town. The location turned a routine trash fire into a subterranean blaze that conventional methods could not reach. Attempts to smother the burn with soil failed because the fractured roof rock channeled air. In 1963, the state funded a flushing project, trenching the bedrock and pumping in 20,000 cubic meters of slurry. Engineers mislocated the trench under a mine of maps, and the fire bypassed the barrier within months. By 1973, carbon monoxide levels inside homes exceeded OSHA limits, and Highway 61 asphalt buckled as subsurface temperatures hit over 300 degrees Celsius, opening steaming fissures that swallowed a petrol tanker. Centralia's geology transformed the fire into a public health crisis. The town does sit steeply on dipping seams riddled with natural joints. Combustion-generated gases rose through the strata, and they entered basements through utility chases and porous foundations. In February of 1981, a 12-year-old boy, Todd Domboski, fell through a sinkhole that had formed overnight in his grandmother's backyard. The escaping steam measured 340 degrees Celsius, and it contained 1,600 parts per million of carbon monoxide. Federal investigators warned of imminent danger, estimating the fire's footprint at 3 square kilometers and a depth of 90 meters, with enough fuel to burn for another 250 years. Relocation here became inevitable. The 1984 Mine Fire Acquisition Relocation Act appropriated $42 million to buy 500 properties, and it moved 1,100 residents. Some homeowners did resist, arguing that ventilation fans and CO2 detectors were adequate, but by 1992 the Pennsylvania governor evoked eminent domain, condemning every remaining structure. As the holdouts left, demolition crews scraped blocks to bare earth, and the borough's zip code was revoked in 2002. Its paved grid slowly reverted to meadow. Only a dozen residents, protected by a 2013 life estate settlement, remain to tend gardens amid misting boreholes that vent an estimated 12,000 cubic meters of combustion gases. Centralia epitomizes disastrous siting twice over. First, a town established on top of a vast, gassy coal seam. Second, a municipal dump placed in direct contact with that seam through an abandoned mine. And a single careless ignition turned a location into a destiny, erasing centuries-old borough and creating a burning void that may smolder until 2300. Where homes and churches once stood, only a warped lattice of cracked asphalt and vent pipes remains, showing how the wrong site choice can reduce an entire community to a cautionary tale, quite literally built on hot coals. Moving on to number 7, the Norilsk Mining Metallurgical Complex in the Russian Arctic. Norilsk exists because of mountain copper-nickel sulfide ore that happens to pierce the Siberian tundra 300 kilometers north of the Arctic Circle. Founded in 1935 as a gulag labor camp, the city was laid out on continuous permafrost that, at the time, was assumed to be permanently frozen to depths of 300 meters. Soviet engineers treated the frozen ground as rock. Apartment blocks and smelters were supported on shallow concrete pads, steam heat mains ran uninsulated in utilidors only a meter below grade, and tailing dams relied on frozen earth as impermeable barriers. The latitude that made the ore hard to reach also seemed to guarantee geotechnical stability. 8 decades later, the location is turning into a slow-motion emergency. Every ground temperature in Norilsk has risen by more than 2 degrees Celsius since 1970. Borehole thermometers now record summer thaws penetrating 1.5 meters deeper than the design assumptions. And as the ice melts, overlying soil contracts, causing a differential settlement of up to 40 centimeters between the column's footings just 6 meters apart. A 2016 survey by the Russian Academy of Sciences classified 57% of pre-1980 buildings as structurally unsound. The nickel smelters fare no better. Hot water discharge keeps the ground beneath the slag furnaces above freezing year-round, so the concrete piles are literally sinking into mud. The permafrost thaw also does undermine pipelines that carry diesel, methanol, and processed fuel over dozens of kilometers on tundra. On May 29, 2020, a corroded support failed beneath a 40-year-old diesel tank at a metallurgical plant. 21,000 tons of fuel spilled into a river, coloring it crimson for 35 kilometers and forcing President Vladimir Putin to declare a federal emergency. Cleanup crews erected floating booms, yet much of the fuel emulsified and vanished beneath the river ice, adding to a pollution load that already made Norilsk the largest point emitter of sulfur dioxide on the planet. The Norilsk planners could not foresee 21st century warming, but the location was always marginal, an industrial city perched on frozen stilts that owes its solidity to ice, 2,000 kilometers away from the nearest paved highway. As the Arctic temperatures climb twice as fast as the global mean, that gamble is failing. The ore body remains, but the ground that holds the smelters, apartment towers, and fuel tanks is turning to sludge. Proof that building a metropolis on permafrost was one of the riskiest location decisions in modern industrial history. Number 6. The Greater New Orleans Flood Protection System. Ah yes, New Orleans. When the French founded New Orleans in 1718, they chose a crescent of high natural levee along the Mississippi River's east bank, barely 1 meter above sea level, yet dry by Delta standards. As the city expanded, engineers pushed canal and drainage ditches into surrounding back swamps, piling the excavated muck into artificial levees that kept river floods out, but trapped rainwater in. By the early 20th century, giant screw pumps invented by Baldwin Wood would move trapped water over the levees and into Lake Pontchartrain, opening thousands of acres of cypress swamp for subdivision. The moment those suburbs rose on freshly dried peat, the ground began to oxidize and compact, sinking by up to 2 centimeters per year. Today, half of the metropolitan area lies 1 to 2 meters below the mean Gulf tide level, shielded from storm surge only by earthen berms and concrete floodwalls. This site is also further cursed by geography. New Orleans sits at the funnel-shaped head of a 32,000 square kilometer estuary where hurricanes moving north through the Gulf drive water directly towards the city. A strong storm surge can enter the industrial canal and, through 2 19th century shipping cuts, pour into neighborhoods that sit lower than a basketball hoop below sea level. Engineers knew the danger. A 1965 Corps of Engineers report warned that a Hurricane Betsy-class event could overtop canal walls, and budget constraints delayed any fixes. The consequence of siting a metropolis in a sinking delta bowl became horribly clear on August 29, 2005, when Hurricane Katrina's 4 to 6 meter storm surge breached flood walls at 50 locations. Within hours, 80% of the urban footprint lay underwater. 1,392 people died, and property losses exceeded $100 billion. Forensic panels concluded that many flood walls had been founded on soft clay without adequate sheet pile embedment, and failures rooted as much in location as in design. Post-Katrina, the United States invested $14 billion into hurricane and storm damage risk reduction systems, erecting over 217 kilometers of new levees, a 2.5-kilometer-long surge barrier across the funnel, and the world's largest pumping station at Seabrook. Yet the delta keeps subsiding and sea level keeps rising. National Oceanic and Atmospheric Administration gauges at Shell Beach show relative sea level rise of 10 millimeters per year, double the global average, because the land itself is sinking 6 to 8 millimeters annually. That means every year the city's 7-meter-tall levees lose almost a centimeter of effective freeboard. Engineers can raise walls, but drainage remains a catch-22. The very pumps that keep streets dry also accelerate the subsidence by lowering the water table and drying the organic soils. A 2023 study by Tulane University found that reducing pumping during minor rain events could cut the subsidence by a quarter. Yet that would leave roads underwater after every summer thunderstorm. The alternative? A massive river diversion to deposit new settlement. It faces opposition from oyster fishers and coastal landowners. Climate projections kind of sharpen this dilemma. A Category 3 hurricane striking just west of the city could generate an 8-meter storm surge in the funnel, overtopping even the post-Katrina barriers. Modeling by the Corps shows that without further elevation, the new system's 100-year protection will degrade to about 25-year protection by 2047. Meanwhile, the insured value of property inside the levees exceeds $500 billion, and more than 1 million residents depend on a flood protection scheme whose margin of safety shrinks every season. Geography gave New Orleans its port and its culture. It also handed the city an engineering treadmill with no finish line, proving that sometimes the worst possible location is a settlement that one cannot abandon, no matter how high the water gets. Number 5. The Three Gorges Dam in China. China's Three Gorges Dam. It's the world's largest hydropower installation, but it's sitting in the heart of the Yangtze River's limestone gorge system that's proved a running demonstration of how geography can keep even the most mammoth project permanently on edge. Engineers picked the site because hard Precambrian bedrock promised an ideal abutment. What the location also delivers, however, is a cocktail of hazards. An active seismic belt that produced a magnitude 6.4 quake just 80 kilometers upstream in 1964. Mountain slopes fractured by 20 million years of erosion and sediment load that's among the highest of any great river on Earth. Those slopes are the first red flag. When impoundment began in 2003, water rose 115 meters in 15 days, saturating the clay seams in the limestone. Entire hillsides began to creep. By 2008, the Ministry of Water Resources had logged 4,700 new landslide sites within a 600-kilometer reservoir. The most notorious dropped 24 million cubic meters of rock into the river, generating a wave that killed 14 villagers and forced 20,000 others to relocate. Geological survey borings now reveal tension cracks more than 40 meters along both banks. More than 250 monitoring stations track tilt and pore pressure. The seismicity was thought to be modest until water filling triggered reservoir-induced quakes. Beginning in 2003 and to 2023, over 3,400 events above a magnitude 2 were recorded near the dam, 10 times the pre-impoundment rate. Most are small, but the China Earthquake Administration's models show that a magnitude 6 event on the fault could register peak ground accelerations close to the dam's design envelope. Engineers have reinforced the right bank spillway with post-tension anchors and installed 500-ton sliding gates that can shed discharge even if the concrete cracks. but each tremor renews the debate over whether concentrating 39 billion tons of water on top a seismographic zone was prudent in the first place. In short, the area gave engineers bedrock, but it also delivered unstable slopes, seismic faults, colossal silt loads, and irreplaceable habitats. Three Gorges still generates 100 terawatt-hours per year, but every kilowatt is balanced against armies of geologists, dredgers, slope inspectors, and emergency planners racing against the physics of a gorge that nature never meant to be a lake. The dam's record output is celebrated each monsoon, yet its location ensures that the struggle to keep the slopes standing and turbines clear will remain as permanent as the concrete itself. Number 4. John F. Kennedy Space Center in Florida. From certain camera angles, the giant concrete flame trench of Pad 39A looks as unshakable as the bedrock that anchors ancient citadels. Yet below the crawler transporter tracks, there is no bedrock at all, only a restless ribbon of beach sand draped across a marsh-muck and lagoon clay. NASA chose Merritt Island in 1961 for clear orbital flight paths and the free eastward push of Earth's rotation. The agency needed an eastern seaboard site where spent stages, toxic propellant clouds, and wayward boosters could just crash harmlessly into the Atlantic. Velocity, not permanence, dictated the pick. The Cape's geology was an afterthought because the Saturn V had to fly before the decade ended, and the barrier island could be purchased outright, bulldozed quickly, and ringed with a modest rock wall that engineers of the day assumed would hold back the sea for generations. 6 decades later, the very qualities that lured NASA — ocean frontage, low latitude, large empty land — have converged with a warming climate to make Launch Complex 39 one of the most endangered pieces of national infrastructure in the U.S. Barrier islands everywhere are mobile, but Merritt Island is notably thin and low. Core samples show a veneer of quartz sand little more than 6 meters thick lying on top semi-liquid peat. The highest natural ground within the Space Center boundary stands nearly 4 meters above mean sea level, while large portions of the wildlife refuge inland sit at 1 meter or less. Before NASA arrived, storms regularly carved new tidal inlets across the Cape, only for them to silt up a decade later. That dynamism is exactly how barrier islands dissipate wave energy. Yet a launch pad, with its flame trench, lighting towers, LOX tanks, and cryogenic feed lines, can't retreat inland or shift sideways as sandbars do. Within 5 years of the first Saturn flight, the Atlantic storms began biting away at the fringe dune NASA had left between the ocean and Pad 39A. By the early 2000s, the shoreline in front of 39A and B had retreated more than 100 meters compared with 1962 imagery. In places, the ocean lapped within 6 car lengths of the crawlerway that carries the rockets from Vehicle Assembly Building to the pads. Storm Surge 2 remains an existential worry. National Hurricane Center hindcast showed that Category 3 cyclone making landfall just south of Cape Canaveral would drive nearly 6 meters of water into Mosquito Lagoon and over the dune fronting LC-39. Yet abandoning the site means surrendering 4 degrees of rotational boost and decades of range safety infrastructure. Advantages neither Virginia Wallops nor Texas's Boca Chica can fully replicate for heavyweight lunar and Mars vehicles. Kennedy Space Center thus embodies the paradox of technological audacity that's rooted in fragile geography. The moonshots that began here rewrote what's possible, but the land itself remains stubbornly mutable, every grain of sand contesting the illusion of permanence. The location delivers performance unmatched by any other U.S. launch range. It is also demanding a rising tribute in sand, concrete, steel, fuel, and bureaucratic maneuver. So far, the gamble is paid, but the odds lengthen each year, and the ledger of sand truckloads, corrosion work orders, and lightning repairs offer quiet testimony to the price of reaching the stars. Number 3. The Run-It Dome on the Marshall Islands. From orbit, the northern tip of Enewetak Atoll looks like a pale green fleck in an empty sea. But zoom in a little bit, and a perfect white lens comes into view. A 115-meter concrete cap that bulges out of a nuclear blast crater. Officially called the Cactus Crater Concrete Structure and completed in 1980, the dome entombs over 73,000 cubic meters of radioactive soil and scrap left behind by America's Pacific Nuclear Testing Program. Engineers selected the site because the crater, excavated by an 18-kiloton device in 1958, was already a 9-meter deep bowl, large enough to swallow the hot debris scrapped from 10 neighboring islets. Filling an existing hole avoided hauling waste thousands of kilometers to the continental United States and cut cleanup costs by 2/3. It also parked one of the world's dirtiest landfills on a slab of porous, storm-washed coral less than a meter above the rising Pacific Ocean, with ocean water lapping the crater wall at high tide and no engineered liner separating radionuclides from the lagoon's food web. Work crews, mostly military personnel in rudimentary protective gear, spent 3 years bulldozing the contaminated soil, laced with plutonium-239, strontium-90, and americium-241 into the crater. They sealed 58,000 barrels of debris in a herringbone stack, then covered everything with a 45-centimeter thick concrete dome poured in 324 interlocking segments. Project managers accepted that groundwater would move freely through the permeable coral floor, arguing that the soil's low solubility would limit migration. Declassified memos showed the designers expected the cap to last 30 years. It's now 45 years old, and climate models predict that by 2050, the highest tide of the average year will reach the dome's rim. A 2013 Los Alamos National Laboratory survey detected plutonium concentrations in lagoon settlements outside the crater, roughly triple the U.S. cleanup guideline, showing that radionuclides are already escaping. 2 geographic facts compound this risk. First, Inuiatak sits at the typhoon belt. A direct hit from a Category 4 cyclone would drive 5 to 6 meter storm surges across the atoll. A Defense Threat Reduction Agency finite element model shows that a surge could scour away the cap's seaward shoulder, turning the dome into little more than a low seawall. Second, the coral foundation is subsiding 2 to 3 millimeters per year, even as global sea rise levels change at almost the same pace. Together, those vectors subtract about 6 centimeters of freeboard per decade. By 2080, much of Runnet Island will likely stand permanently underwater unless massive artificial embankments are built. That's an implausible expense for a republic whose entire GDP hovers around $250 million. Technical options are narrow. Excavating and shipping the waste to a licensed repository in New Mexico would cost at least $1 billion, 4 times what Congress spent on the original cleanup. So Runnet Dome remains, a luminous white oculus visible in every satellite map silently seeping isotopes into one of the planet's poorest fishing grounds. Its creators called it a final remedy in 1980. Islanders called it the tomb. Both labels ignore the reality that coral atolls are not static landforms, but living, eroding reefs. As the Pacific rises, the tomb will eventually sit beneath water, unless somebody moves the waste or builds an unbroken ring of seawalls around a speck of coral in the world's widest ocean. The dome's very existence thus testifies to a disquieting calculus. The cheapest place to hide nuclear waste in 1977 was also among the worst, because nothing about its geography can keep the ocean out forever. Number 2, the Bataan Nuclear Power Plant in the Philippines. In the geothermal archipelago of the Philippines, volcanologists maintain a map known as the Pacific Ring of Fire Danger Zone. Squarely inside it, on the jungle-clad slopes of Mount Natib, a dormant volcano with a 6-kilometer caldera, sits the Bataan Nuclear Power Plant, the only commercial reactor facility ever built in Southeast Asia, and simultaneously the only one never to load fuel. Planned in 1973, rushed through construction under President Ferdinand Marcos, and mothballed after the Chernobyl disaster. The BNPP is a weathered monument to what can go wrong when a megaproject is planted on an active subduction zone. 16 kilometers from a caldera and 25 kilometers from the epicenter of the 7.8 quake that shattered central Luzon in 1990. Site selection was political from the outset. Westinghouse lobbied Manila with promises of U.S.-backed financing if the plant were placed on government-owned land at Napot Point, a rocky headland facing the South China Sea. Geologists flagged a swarm of microfaults branching off the Manila Trench, which dives deep beneath Luzon at 10 centimeters per year, but the Presidential Committee overrode them, accepting Westinghouse's assurance that a magnitude 7 event could be withstood. Engineers then designed a single 620-megawatt pressurized water reactor onto a seismic Category 2 foundation, less stringent than the Category 1 demand for plants in California. Construction quality mirrored this rushed site study. In 1979, a U.S. Nuclear Regulatory Commission audit found poorly welded rebar and voids in concrete samples. Piping support bolts were misaligned and containment tendons were overtensioned by up to 30%. Marcos nevertheless pushed for completion, doubling the budget to $2.3 billion, 10% of Philippine external debt at the time, because oil prices had quadrupled and he needed a showcase of energy independence. Then, geography continued to mock the site. In 1991, Mount Pinatubo, 40 kilometers north, erupted in the second-largest volcanic event of the 20th century, dumping 10 centimeters of ash on the powerless reactor dome, and proving that regional volcanism was not hypothetical. 9 weeks later, a magnitude 6.2 aftershock triggered a lahars that buried villages only 30 kilometers away. Had the plant been operating, the ash alone would have forced immediate scram and placed fresher than design-based strain on cooling water intakes already prone to biofouling. Since mothballing, the structure has deteriorated. Tropical humidity corrodes the switching gear. A 2013 inspection found 60% of electrical cables unserviceable. Sea level rise now pushes salt spray 200 meters inland, rusting the reactor building air intakes. Local opposition counters that Mount Natib's magma chamber inflates by 2 millimeters per year, measured by INSAR data, and that no retrofit can relocate the caldera. Critics note that the emergency planning zone intersects the highly populated Subic Bay Freeport. An accident could force the evacuation of 500,000 residents on the same roads tourists use. Number 1. Turkey Point Nuclear Generating Station, Biscayne Bay, Florida, United States. At first glance, the mangrove flats 40 kilometers south of Miami seemed like an ideal place for a power plant. Cheap, empty land, year-round access to warm seawater for cooling, and a downwind flight path over unpopulated Biscayne Bay in case of accidental releases. So in 1967, Florida Power and Light began pouring concrete for 2 pressurized water reactors, units 3 and 4, on a peninsula barely 2 meters above mean sea level. Half a century later, the same geography is turning the 1,600-megawatt facility into a textbook example of why low-lying karst coastlines are terrible spots for critical infrastructure. The first problem is the elevation, or the lack of it. Tide gauge data at nearby Virginia Key show relative sea level rise of 9 millimeters per year when land subsidence is included, triple the global average. Add storm surge and the margin vanishes quickly. Hurricane Andrew's 6-meter wall of water in 1992 stopped at the plant's earthen berm only because the eye passed 10 kilometers to the south. A Category 4 track just 5 kilometers north would overtop the existing defenses, according to 2019 Army Corps modeling. Unlike inland reactors that rely on concrete dikes, Turkey Point sits on Miami oolite, a porous limestone. Even if engineers raise the seawall, surge water can percolate underneath and emerge on the dry side, which just would nullify the barrier. Elevation ties directly into cooling. Instead of mechanical towers, the plant relies on a 270-kilometer network of opened, unlined canals that snake across 24 square kilometers. Essentially a giant radiator whose water volume equals about 9,000 Olympic pools. Evaporation concentrates salt, summer heat waves push canal temperatures above 38 degrees Celsius, which would force operators to dilute the system with up to 380 million liters of fresh water per day pumped from the Floridian aquifer. The canals now run 20 parts per thousand, 2/3 the salinity of seawater, and this brine is seeping through the limestone into the adjacent aquifer, a drinking water supply for 3 million people. Turkey Point's operators have applied to run the reactors until 2053, by which time NOAA's intermediate scenario predicts an additional half-meter of sea level rise. Engineers can add pumps, berms, and sheet piles, but they can't change the porous limestone or flatten hurricane tracks. The plant's location, chosen for cheap cooling water and open ocean on 3 sides, now sits at the very convergence of rising seas, salt-intruding aquifers, and increasingly frequent major storms. Every kilowatt that the reactors send to Miami's neon skyline carries a quiet surcharge, escalating maintenance, groundwater management, and storm hardening costs required to keep a nuclear complex running on land that geologists say is inexorably returning to the sea.